Hello, everyone. In this lecture, I will be introducing a tool that I find particularly helpful in the early stages of Bayesian data analysis called causal diagrams. My objectives for this lecture are to give you a framework to use your scientific knowledge to guide your data analysis, as well as a helpful diagramming technique to model causation in a system. There are a lot of useful resources on this topic. I really enjoyed this playlist by Leslie Mint, and there's also some lectures from the Statistical Rethinking course, which are very helpful. So the area of causal diagramming comes from a field called causal inference, and all this means is it's a formalized process for determining cause and effect relationships in complex systems. And it's really the core principle that we use to design and analyze experimental and observational studies. In experimental design, you might not call it causal inference, but that's what it is. And there are some helpful approaches that draw from information theory and graph theory and some of the terminology from there. So in causal inference, we think deeply about the distinction between association and causation. You've probably heard the phrase correlation does not imply causation. Well, that's also true that lack of correlation does not imply lack of causation. Here I'm using association instead of correlation because it's a more general term. So just to illustrate with an example, so let's say thinking about the relationship between eating ice cream and subsequently getting hives. So causation would be if I'm allergic to ice cream and I get hives after eating ice cream, then eating ice cream gives me hives. That makes sense. But you could also have causation without correlation. If I'm taking an antihistamine that prevents hives, then I'm still allergic to ice cream, but I don't get hives after eating it. You can get correlation without causation. So let's say, for example, I'm allergic to the floor wax in the ice cream shop. So every time I go there and eat ice cream, I get hives, even though I'm not allergic to ice cream. And then finally, you can have lack of correlation and lack of causation. So eating ice cream doesn't give me hives because I'm not allergic to it. So this sort of table I could convert to a diagram. So let's say in this causal diagram, I have my treatment, let's say, eating ice cream, and my outcome, developing hives. Um, and that causation is caused by my ice cream allergy. And we have another variable, whether or not I've had an antihistamine, and that prevents hives, but is distinct, separate from eating ice cream. An additional variable, whether or not I've been exposed to floor wax and have a floor wax allergy. And then finally, eating ice cream can be a causal factor for floor wax exposure because I go to the ice cream store where they use the floor wax that I'm allergic to. So this basically is a diagrammatic way of showing all the outcomes from that previous table. Um, so this is what's called in graph theory a directed acyclic graph. So each of these variables is called a node, and usually in a statistical model, we're thinking like the nodes would be some kind of random variable. And I've put the possible values, these are all binary. Um, and then the relationships between nodes are called edges. In a causal diagram, they specify a causal relationship between variables or between nodes. So this term directed acyclic graph is a little jargony, but it's actually highlights some important ideas. So first, the term directed means that there's only one direction of cause and effect. So in an undirected edge, there could be possibly a two-way relationship between variables. For example, you may have heard the phrase, which comes first, the chicken or the egg? The chicken lays the egg, but the egg produces the chicken. This is not very easy to deal with when we're actually doing statistical modeling. Um, so a better way to think about it would be the chicken causes the egg grows up into a chick, and perhaps then the chick might become another chicken. So This, we want a directed graph, not an undirected. The second part of it is acyclic. This is a graph theory term meaning there's no feedback loops. So in a cyclic graph, we might think about the phenomenon where the more sweets I eat, the more I crave sweets, and the more I crave sweets, the more sweets I eat. Say that 10 times fast. Um, for building using inference or using these graphs to develop statistical models, we can't really have one variable feeding back into another one. But if we have this sort of feedback loop in a system, we could model it in an acyclic way by separating out one of these into, let's say, another time step. So craving sweets at time zero and then eating sweets at time zero influences whether you crave sweets at time one. And this we can model with some kind of time series, but these have to become separate variables. So going back to our hives example, um, causal diagrams are a really helpful starting point for building statistical models. So here, the outcome of interest is getting hives, and all the arrows pointing to this, all the connected nodes, are possible predictors. So we would say the probability of getting hives is some function of whether I've eaten ice cream, been exposed to floor wax, or taken an antihistamine. Um, so this is kind of a silly example. So what I'm going to do now is walk you through a causal diagram process for an actual agricultural data set. And hopefully this will be a model for you to start to implement this process in your own work. So the data set that I will be using is on the birth and weaning weight of Dorper and red Massey lambs, um, sheep in honor of Professor Frederick, who's a sheep farmer. So this is a data set from the Agridat package that's freely available. So the main research question from this data set would be is how does the genotype of the lamb influence its birth weight, and weaning age, which as a non-sheep farmer, I assume these are agronomic traits of interest. So I can look up the information about my data set, um, like here, and there's help documentation with all the variables and experimental design, whatnot. But I can use this to start building my diagram. So here's my question. Um, my treatment variable is genotype. I have four possible levels, the two heterozygotes of Dorper, and then the two homozygotes, Dorper and red Mossy, and the heterozygotes with either the mother or the father being Dorper. And I've got my outcome variables, birth weight, and wean age. I've included the units here to indicate, these are all continuous variables, and these are in the same units. And my direction of causation, I'm hypothesizing that genotype causes some effect on these three outcomes. So I can express this in as a function. So here, birth weight, wean weight, wean age, these three outcomes can be expressed as a function of genotype. But if we think through with our science brains a little bit, we might realize that there are other variables besides genotype that are going to affect these outcomes. There is the sex of the lamb, which is independent from genotype. So if we add that as a covariate in our model, now we can express these as a function of genotype and sex. There's also the year the lambs were born. So the environmental conditions may have differed in each of these years, and that may have affected these three outcomes independent of genotype or sex. So now we've added that to our model. And then finally, the outcomes that we're interested in aren't necessary, they're not going to be independent from each other, just if you think it through. For example, a lamb with a higher birth weight may have a higher wean weight, independent of the direct effects of these other variables on wean weight. Similarly, uh, let's say there could be a relationship between birth weight and wean age. Maybe lower birth weight means they have to wean longer, so they're older. when they finally wean, or there could be a relationship between age and wean weight. Um, you can like lambs that are more attached to their moms and wait longer to wean may be older when they do. So, in any case, with all these relationships, we can adjust the models to thinking about now birth weight. We've got three arrows going into that genotype, sex, and year. Wean weight, we've actually now have five arrows coming from our predictors and the other two um, birth weight and wean age. And then this one, we've got four arrows. So this process can be helpful for designing our analysis and kind of unpacking the complexity. A few topics that I want to point out. One is that this concept of which variables treatment versus covariate versus outcome really depends on the design of the study and the question that you're interested in. So, you know, it's another way of distinguishing variables that's used in graph theory is exogenous versus endogenous, or in experimental design terms, we might call genotype, sex, and year independent variables. So in this case, they don't have any nodes feeding into them, so they don't have a parent, so to speak. Um, versus endogenous, which have some kind of parent or causal directed node within the system. Um, and so another issue I want to point out is that at this stage, it can be useful to list out the units or even just the data type, because that's going to affect how you model the variable and the kind of data processing that you're going to need to do to build your models. And then finally, an important idea is that there may be variables of interest that aren't observed in your system. These are typically called latent variables. I couldn't think of a great example for this one, but let's just say um, the quality of the food is going to affect all of these things, and maybe there's some variability in food quality that's unrelated to anything else. So I hope that this process is helpful to you. I've put together an exercise where you will go through this whole process with a different data set, perhaps one of the ones in the AgriDAP package. And I hope that you enjoy it. All right, thanks.